assignments on Friday.
Yes.
All right, you got it. I just reminded them about test corrections. They were supposed to be turned in on Friday, but some people were absent, and to be honest, I didn't grade them yet anyway, so there's a little bit of an extension of grace. Get them into the folder by the end of the day. Read the note on the sideboard. Just throw it in period 5. Oh, I thought I opened it. Didn't I open period 5? Okay, but you were in your notes, and we are in section 10. Oh, I thought we were still in 10.1. I was like, wait, we're in 10.2. And last week, what was the deadline, the due date for the homework in 10.2? Next week. I wasn't very precise because I needed to see how we did. So we are in section 10.2. We are somewhere towards the end-ish, and I'm hoping it's due tomorrow, but we'll see how today goes. But my question to you as I started recording, what were we doing in this example on Friday? Yeah, we were making a Taylor polynomial. Do we have to make it like look like a geoseries, like how we started chapter 10? No, because we have this really cool formula that says, give me any function f. Seemingly give me any function f for whom their derivatives exist. Oh, what would not be a good function to use for a Taylor polynomial? Piecewise, okay, that would be messy for taking derivatives, but what else? Whose derivatives would not be very conducive to an infinite derivation or an infinite series that's based on derivatives? Huh? Actually, e to the x is great because its derivative is easy. I can just keep on doing it. But keep thinking. Think L'Hopital's. L'Hopital's taking derivatives of top and bottom. 1 over 1 minus x would be nasty to take the derivative, so to do quotient rule and then a quotient, and then another quotient. Well, power rule, then quotient, then quotient. Maybe just power rules. So quotient rules will be nasty. Product rules will be nasty because if you have to take a derivative of a derivative of a derivative, oh. But who can you not keep taking derivatives of forever? Constant, but even bigger than that. Polynomials. Don't their derivatives run out? Right? What was the term that we used earlier this year as far as like the ones where you take derivatives until... wow, I can't think of it. Not irreducible, huh? Yeah, derive until it dies. Derive until inconsequential? That's not the word I'm looking for. Derive until basically doesn't have any meaning anymore because they're all gone. Oh, there's a term. I'll try to think about it. Anyway, can't think of the term. Maybe it was an AD. But either way, I taught it this year, so I should remember it. But polynomials, oh, why make a polynomial of a polynomial? It's already a polynomial. Oh, okay. Well, then we won't do that. But anything else, can you keep taking derivatives forever? ln, you take a derivative and it's 1 over, and then you have to do like a power rule, quotient rule, etc. E to the, you can do it forever. Sine, you can do it forever. Yeah, you can take derivatives forever of basically everything but polynomials. So anyway, we're making polynomials out of non-polynomials. That was kind of the point of that whole discussion. We're making polynomials out of non-polynomials. So we just need to know a function, and we just need to be able to find its derivatives, and we just need to be able to plug into our formula. So who was our function at the end of the day on Friday? ln. ln of x. At 1, not at 0. How can I see the at 1 when I'm looking at the function? Horizontal shift, right? It's been a horizontal shift to the right one. So yeah, c equals 1 up there I can see in the problem, and in the actual series I can see it with x minus 1. What does this notation mean again? P sub 6? Just a quick reminder. Catch your ride up because it's gone. To the 6th. That's good corrections. The 6th what? To the 6th prime. The 6th prime. What? Good. The 6th degree Taylor polynomial means to the 6th prime, which could be x to the 6th, but it depends if you plug in like an x squared. It might not be. It might be x to the 12th. Anyway, The 6th degree Taylor polynomial means go in the formula to the 6th derivative, and that term. To approximate, we were using it like we used to use tangent lines to approximate a value. What did we see in our calculator if you were to go back and watch the video if you were gone on Friday, or for those of you that were here, how close did these approximations get? So close that now we second guess our calculator and what it's actually doing whenever we ask for a sine, a cosine, an ln, or an e. Is it actually plugging into those, or is it just using a polynomial approximation? Anybody Google it? Google it. Google it. How TIs are programmed. Anyway, give me back. Did we actually use this? I don't think we finished. We made it. We simplified it. What did we not do? We didn't use it to approximate. So therefore, how do we finish off this problem and then proceed forward to the next problem? We have to plug it in, So our P6 of 1.1, which is approximating our ln of 1.1. Wait a minute, can we use our calculators to help us out, maybe? I'm not saying the AP would always let us use our calculator to do this, but I am saying we can, just for sake of simplicity. If we were, is there a way to shortcut how we type this in? Yeah, I mean, we could put the function and then just use like y1 of, which would be great and all if we were trying to approximate more and more and more. But if we're just doing one approximation, we might not need to write it all the way out. But just because, I erased it all for pre-calc. Oh, no, that was for calculus. They're doing integration as net change. The weird one with the air conditioner and like the function of temperature outside, and then like you have to pay a certain amount for every degree that it's over 78 degrees in whatever time interval. Anyway, we were doing accumulation, we were doing integration as net change. Hey, you see it up there, right? That's kind of important. You need to still remember that. Okay, coming back. Sorry, Taylor polynomials. We're going up to the 6th, right? Okay. So then we have our, is it 1 plus? Nope, that went away because it was 0, yeah? ln of 1 was 0. Okay, so then coming back. We have x minus 1. I'm just putting it in so that we could do it multiple times if we wanted to. And then I think it's all addition, right guys? No? Do we have some subtractions? Why? Why subtractions? When you take derivatives of negative powers of negative exponents, aren't we going to get subtractions, and so it's going to alternate every other? Indeed. Look at that vocabulary. Sounding smart. Being ready for college. Okay, so minus. We have x minus 1, quantity squared. And then we have all over 2 factorial, which is 2, but we had to do some simplifying craziness, but it was still 2, right? Then 3, then 4, then 5. Did I not put minus? Let's see into the process. Let's get back. Minus. And then you guys know we can get to the end of an expression by hitting second and then over, and it pops it to the end, right? Saves so much time. Or second to the very beginning, pops it way back, pops it way over. Plus, you're welcome. Alpha, y equals. Where are we going? X minus 1 raised to the 3rd power. All over just 3 after we simplify all the factorials and everything, right? And then we're doing minus again, so now we have x minus 1 to the 4th. All over 4. Where am I at? A plus or a minus? Plus? Only they copy and pasted. Oops, I didn't want that. Oh no! That's okay. I can go right back where it was. X minus 1 to the 6th. What am I supposed to be using this to do again right now? Approximating where? ln of 1.1, because this is the Taylor polynomial for who? ln x at 1, or around 1, right? X minus 1 to the power of 6 all over 6. Whew, that took forever, but now I can use it however many times I need. So, setting quit, let's go ahead and do y1 of 1.1. What are we trying to compare it to? ln of 1.1. Wasn't that great? I mean, it's still pretty dang good compared to a tangent line, right? But I think might need a few more degrees in our Taylor polynomial to make it look exactly the same. But what if we were to go ahead and maybe instead of doing 1, which once again, it's a little bit messy, I agree. It's a little bit off. We could see if it's any better of approximation if we go a little bit closer. And then we could do ln of 1.05. Well, that's not bad. That's not bad. That's pretty good. And I guess the calculator could probably center at like 1.1, 1.2, 1.3, 1.4. So it wouldn't even just be centered at like 0, 1, and 2, etc. But wait a minute. What if we were to, so we're like, okay, it gets pretty far off as soon as it gets to 1.1, right? Let's see. What am I trying to prove? Give me a second. What if I was to go back? And what if I was to change this instead to, oh no, it's not going to be as pretty. What if we wanted to have this be centered at 2 or 3 or 4? What would change in our equation? The C. X minus 2, x minus 2, x minus 2. Is that the only thing that would change? Or can I literally just come here and can I plug in minus 2, minus 2, minus 2 and have it centered somewhere else? Yes or no? Do you understand how Taylor polynomials work? If I wanted this centered at 2, showing you that ln's are continually increasing at a decreasing rate, which means the farther you center it, the farther in you center your Taylor polynomial, the closer it will be for a longer extended period of time. Only at 1 do we have a huge change where we have a lot of error. If I wanted to center this at 2 or at 3 or at 4 and show you how going 0.1 will just end up being a better and better and better approximation with a 6-degree Taylor polynomial, what would I have to do besides changing this to be 2 in every single term? The derivative. Because isn't this a numerical derivative? We find the derivative and we plug in, but what do we plug in? Yeah, we have to plug in C. So I have to come back and do f prime of 2, f prime of 3, f prime of 4, f prime of wherever I want to center it. So sadly, I can't just quickly change where it's centered at. I'd have to go through and rework my entire Taylor polynomial, basically coming back and saying, okay, I have my 2 factorial, 3 factorial, 4 factorial, but what is f prime of not 1 anymore, but 2, or f prime of 3, or f prime of 4? So long story short, I can't exactly just quickly show that. It's a good idea. Except it would take more time to form. Anyway, but Taylor polynomials, can they approximate sines? Yes, we saw that Friday. Can they approximate ln's? Yes, we saw that Friday. If you want to see a graph of this, we just need to think about who ln is. I'm going to be snazzy because I want to see the ln first. I'm going to take him away. I'm going to put in ln first, if I can get him over. And then let me go get y1 and make him y3, just because I'm going to be petty like that. There we go. And now let's look at my zoom and my standard. There's my ln. Aww, well that's no fun. Is it not going to do it for me? Oh, you know what? Hold on, I know why. Let's make the window not go negative because my Taylor polynomial is going to be mad if I do that. Let's go here. Let's do 0.1, which exists. It's not infinite. To, yeah, let's try that. Is that better? Oh, stink. Really? They just don't like that. Okay, fine. It was a good idea for a whole half second. Okay, clear. Let's go back. Let's select. We'll do it the old-fashioned way. How close is that to ln? Pause. It's graphing for forever. It's graphing for forever. All right. Oh my goodness gracious. Didn't know it would take this long. Oh, it's not ln. Okay, I get it. I know it's not ln. But hold on. Here's ln. Ooh. How close is it for a while?
Kind of close. Hey, did we have some special McLarens back here somewhere? For e to that and... Oh, I know I showed you on Friday. It's ahead. It's not behind. Here we go. What does the one for ln say? Not quite the entire thing. You see it? LNs are coming from the geo series. Since they're coming from the geo series, they have something similar as far as an interval of convergence only being for a certain amount. So the bummer is we're not going to have like sine and cosine. We're not going to have, or e to the x, we're not going to have for all real numbers as our interval of convergence. But it is going to be converging the infinite sum perfectly to the ln just within a certain interval. Anyway, all that to say, we can make Taylor polynomials for ln's. Yay! Okay, what else? What if the AP were to give you something like this? What kind of question, huh? Yeah, they've done all the work for us! Don't we love these ones? If you get the concept. If you don't get the concept, you're screwed. But if you get the concept, what do they want us to do? Plug it in, plug it in. Plug it into what? Okay, what's the formula? I know it's a G and not an F, but still. G can be approximated by P3, which is, you guys see kind of like the Euler's method idea of like the actual is approximated by the approximation, which is equal. Sorry. G of who? Oh, you're plugging in G of 2. I'm just doing the notation first. Plus x minus 2 because we're centered around. You guys see it? Right? Okay. And then keep going. See it? It's going to be easy to forget that because the formula is technically over 0 factorial. It's 1 over 1 factorial is 1 over 2 factorial. Right? And then HA, we keep going until we have which derivative?
Third derivative.
Got it.
Yes. So over 3 factorial? Is that G to the 4th prime of 2 equals -5?
G3.
Is that G?
Third derivative. Because it's G prime, G double prime, G triple prime. So now at this point, hey guys, if this was an FRQ part A, wouldn't it be awesome? Because all you have to do is just throw in the 3. Throw in the, box is going to be done as soon as you get it in. Get it in. G double prime is 7. Right? If we get the idea, it's awesome. Is that good?
We like those.
Ooh, what if they gave you... Oh, wait, I'm getting into a garage. We're not quite ready yet. They could give it to us listed out in points. They could probably, I don't think I've seen them give us a table of derivative values. That'd be messy. They would have to do different derivative values. I have seen them give you a graph of a particular derivative, but that's for a future formula where you need to have like the 5th or the 6th or the 10th. I think I've only seen them list out the clues because they have to give you different derivatives, and that's awkward to give you in any other format besides just listing them out. Okay, so that's a kind of nice thing that could appear. It's like, hey, we just have a new formula. If they give us clues, sweet, we'll plug it in. What's coming on or what's going on in this example, though?
Each third degree of e to the x. Find the limit of...
Wait, why are they having me do lots of work to find a limit? Why not just plug and show? Oh, because it'd be a L'Hopital's, yeah, because it would be 0 over 0 and they keep going. If it was CalcBC, we wouldn't be able to keep going without L'Hopital's, right? And if it's L'Hopital's, okay, well, pause. Hold on. Let's try to do what they're telling us to, because if they ever put these in the directions, we're going to have to show the Taylor polynomial. We're going to have to show using it. So somehow they want me to take this limit, eventually. Take this limit as x approaches 0, e to the x minus 1, all over 2 of x. And we want to say that's approximately the limit as x approaches 0 of We want to get the third degree Taylor polynomial for e to x and substitute in for e to the x. It's approximate, it's not exactly e to the x. Subtract 1 over 2x and just see what happens. Hold on, to make the Taylor polynomial for e to the x, without just memorizing that endeavor card that I did tell you was out there as far as common Taylors or Maclaurens for series. Ooh, good thing is this one's near 0. This would be one of those memorizing ones. Let's just review how to find Taylors. Why am I going to come over here and say e of, why am I doing this? Although I guess it's a little silly, because what's true? Do we mind e to the x? Not at all. Because what's going to be true about every single one of these when we're doing them at x equals 0? It's just going to be e to the 0, which is 1. So when I come over here to plug into my third degree Taylor polynomial for e to the x, isn't it just going to be e to the 0, which is 1, plus e to the 0, which is 1 times x minus 0? And then e to the 0 is 1 times x squared, all over 2 factorial plus, ooh, I like e. I like him a lot. So wait, I'm going to take this, the third degree Taylor polynomial for e. I'm going to plug it in here. So I'm going to end up with 1 plus x squared all over 2 plus x cubed all over 3 factorial. What's going to happen to my 1s? Cancel. What's going to happen to my x? Reduce away, right? He's going to reduce away one of him, and then take him totally away. Oh, can't I just plug it in? So that's just going to be 1 plus 0 over 2. What would L'Hopital's have told me? What's the derivative of e to the x? E to the x over derivative of 2x? 2. And then plugging in 0, e to the 0 is 1 over 2 is 1/2. Huh. I wonder if Wolfram Alpha uses L'Hopital's in order to actually solve for limits when you ask them what the limit is, or whether it uses Taylor polynomials. I'm just saying, I wonder. Google it. Anyway. But to do L'Hopital's, don't you have to be able to find derivatives?
I mean, like, it's like but then you just need to look at so easy.
Now, you can't numerically find derivatives, but Lorenzo's still pondering how they numerically are able to find derivatives. But anyway, maybe he'll Google it. Coming back. How about this guy? This sounds a little AP-ish. Given that, P sub 2, wait, now I can approximate with quadratics, not just tangent lines? This is interesting. Okay, second degree Taylor polynomial for some function f, who, I don't know, about x equals 0. What can you say about the signs of a, b, c if f has the graph pictured at the right? Greater than, less than, or equal to. Who's A? According to what I know about Taylor polynomials. Not f of c, but f of 0. Who's B? Who's C? At 2 factorial. It's not going to mess you up in this problem, but it definitely will in future ones. Be careful, over 2 factorial according to our formula. True?
Yes.
How do I know this? Because it's x minus 0 with the primes and okay. Huh. And that's f. So what is f of 0? Positive. What? Yeah, because it's over the axis. It's some sort of positive, maybe it's 1, maybe it's 2, maybe it's 10, maybe it's 100, depending on the scale. I don't know, but it's something positive. But how about f prime of 0? Positive 2? Why? Since
f is increasing at x equals 0. Look at that tangent line. Of course it's going up. Or I should say, just look at my curve. Of course it's going up. How about f double prime? Why negative? Look at us making you review pre-calc. Anyway, CalcBC. That's a great question. You know, Taylor polynomials and increasing, decreasing, and concavity all in one fail swoop. Fun. Keep going. So, we've seen this guy. Remember, sine has odd symmetry. We've seen this guy. Remember, cosine has even symmetry. We've seen e to the, oh yeah, he's the nice one. All the derivatives are the same. We've seen this one from Geo. Remember, start at 1 times x times x times x. This one, wait, why is he, oh, that's right. Ratio is negative x times negative x times negative x times negative x. We've seen this one because we integrated that power series a little while back. So integrating term by term. And we've seen this one. No, we haven't. Tangent inverse. Well, yeah, that's what I was thinking. Tangent inverse is the integral of 1 over 1 plus x squared, which could be the Geo series with x squared plugged in. So we could have done x squared, 1 minus x squared plus x to the 4th minus, and then integrated term by term. That's how they would have done it. Wait, nah, they would have built the Maclaurin, because they would have taken his first derivative, second derivative, third derivative. No. Let's not take his first and second and third derivative. Let's see that he's actually the integral of 1 over 1 plus x squared and use the Geo series at x squared or with a common ratio of x squared. Okay, I think I had you guys take a picture of this on Friday. Perhaps, possibly, perhaps. I have no idea where we're at as far as endeavor cards. Hold on. We had Taylor Maclaurin polynomials. I think I want to make that one card. We didn't label that though, right? We had power series. That was a card, right? These are polynomials. We have a series card coming. I just want you guys to have this one for the sake of the coefficient. This is super important, the coefficient of the x minus c to the nth term. And the idea that polynomial is approximately f of x. I want you to get somehow the approximate symbol on this card. The key is that polynomials only approximate. Polynomials end. Polynomials are finite. We're getting towards the Taylor Maclaurin series where they are perfect. But this is, endeavor number. Ratio root was the end of chapter 9 OT. We had power series. Was there anything else we had besides power series? Did we make a card? I made a card. Oh, this was the one I made. Okay, so endeavor number 25, this is endeavor number, Taylor and Maclaurin is 26, and then the one that we're on, John Gass, 27. Oh, I went the wrong way. Sorry, guys. I'll see it. That was 25. This next one, Taylor and Maclaurin both. I'm adding pages now. That's cool. Let's add those pages. Endeavor number 26. And that makes this one endeavor number 27. Now, some of you might realize that you don't necessarily need absolutely everything on this page, but I do need you to know the nth term. I think the nth term is helpful just because these are ones that are commonly put on the AP. I grabbed this from Mr. Calculus, who has like the highest pass rate of ABM in BC for the last however many years, pretty much out of the country. He's the one that everyone goes to figure out what the FRQ solutions were to the previous exam before the actual AP people put it out. Anyway, in his experience, he's like, yeah, these ones are good. Pretty much. Because they, a couple of days after the AP, they released the questions for AP teachers to see. He goes through, makes his own solutions, and shows them. Yeah, posts them online. And then he goes and grades the AP every year in Florida. Yeah.
Good question. Will there ever be a moment where like they're evil and they make us find like 8, 10?
I mean,
Yeah, like,
they just capitalize on her money.
It could possibly be helpful, especially if one of these is alternating and you're using it and they're trying to ask you about the error, then you would want the next one. Does that make sense? Yeah. I'm sure there is. But he also has like a whole calculus team at Diamond Bar, is that what he's teaching? He's basically like built the entire like public education system around getting kids ready for calculus. Like he went to the middle school down the road and basically said, I need better kids in my math classes, let's work on you. He probably went to the elementary schools too. He's very ambitious. Awesome guy. Huge personality. Plays like rock music so that the kids are like getting ready to go into class every day and it's blaring down the hallway. It's quite the system. Yeah, he rocks the movie. Alright, you guys got it? Oh, you're writing it down, you party pooper. You're supposed to take a picture of it. But John, all that to say, they do like asking you, think of last year, the 29th, 27th, whatever derivative you were supposed to find, they do like asking you for a derivative of a function that you need to think of the Taylor series and what would be occurring way down here to find it. Yeah. It's another way to find a derivative, especially if it's of a complicated function that there's no way you could take that many derivatives in the time allotted. But if you knew it's Taylor, that's Maclaurin or it's Taylor, you could jump there. Or even better yet, if they give you one of those AP ones where they don't give you the function, like in example number 5 or example number 7, they might not give you an option. You have to use what they tell you to figure out the derivative because you can't solve for it by hand at all. Okay, it's on there. So you guys define, we're getting pretty close to wherever homework is supposed to. Oh, look, okay. So, what if? Oh. Wait a minute. Wait a minute. See the point. To find a Maclaurin polynomial, don't I define like a first, second, third, fourth derivative? A first, second, third, fourth. Product rule upon product rule upon product rule. Chain rule upon product rule. Well, no, product rule. Anyway, do you really want to take 4 derivatives when it's like going to be product rule after product rule?
No, we have to.
However, who's behind the scenes in this? Signs. I mean, yeah, kind of. Signs behind the scenes. Otherwise, we just plug in 2x. Wait, who's sign? Sign's odd. If sign is odd, then isn't he the one that goes x minus x cubed over 3 factorial plus, wait, how many things are supposed to be? Here's 4 non-zero terms. X to the 5th over 5 factorial minus x to the 7th over 7 factorial. So what's different if it's sign of 2x? Why am I putting approximate? Because I'm ending it. Yes, sign converges for all real numbers if it's infinite, but it's not. So I say, okay, it's approximate. And I say 2x minus 2x cubed all over 3 factorial plus 2x to the 5th all over 5 factorial. You guys want to be pondering that one? Minus 2x to the 7th over 7. He's the product rule that you would not want to take multiple derivatives of, although those of you that took 27 derivatives last year,
Bad.
You're welcome. Love you. Need it. Okay. Now what? Who am I building for? Cosine. Nope, not G. G is this dude. Who's cosine? He has even symmetry. What? That's supposed to help? Yeah. Because he's not going by odd powers, he's going by even powers. So wouldn't he be 1? Minus x squared over 2 factorial plus x to the 4th over... You guys double checking I'm right?
Yeah.
Minus x to the 6th all over... How many terms? 4. Would you rather do G prime, G double prime, G triple prime? Wait, you'd have to go all the way up to the 6th prime to find this? Of a product rule, and then another product rule, and then another product rule, and then another product rule? Or would you rather just say, look, just do times x? How easy is times x when you have a polynomial you can just distribute? You see it? Times x. Got him. Times x. Got him. Times x. Got him. And I didn't have to do any product rule. 4 factorial. It looks like a sign, but is it? Couldn't be. Why? Not sign, but oh, is it close? Or you would have taken 6 derivatives and product rules. How about this guy? Or e to the u times u prime, and then a product rule, and then another product rule of a product rule, and then you have chain rules in there too. Or just think, who is he building upon?
More.
E to the x. It would be power rule if you took the derivatives and if you did this the hard way. Or, who's e to the x?
E to the x.
Okay. But his Taylor. Well, technically it's Maclaurin because it's about
1
plus x squared over x.
We love him.
Squared over 2 factorial.
So what do we do if we have 4? Wait, can we do this all at once? Times 4 with an x squared?
Oh. Okay.
Times 4.
Yeah.
Times 4 with an x squared. Ooh. Now what? Times 4.
X to the 4.
Squared, x to the 4th. And then times 4.
4x plus 3.
With the 3.
Yeah.
Now, guys, I'm doing all these long answers to get to the man style. What are they going to do? Simplify, make it match, actually see that it's a 4 over a 2 factorial and reduce it, make that x to the 4th and x to the 6th, make it a little bit prettier. True? Dun, 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 dun. I'm just saying if it was multiple choice, you would have to say. So, homework. Well, we don't have tons of time. But I have it open over here. Homework. Remember how last time you guys were like, okay, let's go do homework, and then you all came back and said it sucked. Okay. Hold on. You guys ready? What if I zoom in real fast? You can see the circle problems. The circle problems are the ones that you have for homework. Let's zoom in. Bloop, 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 bloop. What does the first section say? Should we know how to do this? Yeah. Wait a minute. I have to find f prime, f double prime, f triple prime? Maybe. Maybe not. Can you figure out how to do a square root of 1 plus x squared? Now, it'd be nice if I would have given you that one. But I didn't. I think you actually have to take derivatives for at least one in homework. But pause. Wait. But now what? Now what? Okay. This one, I'm making you do f prime, f double prime. Wait, how many primes are you going to have to do?
4.
Nice. And then plug in. But then, what had you better be thinking as soon as you start getting down to here? Can you start with a basic Maclaurin and build up? Now, pause. Can I tell you one warning?
What?
This whole special, like, yay, we know who they are. What kind of series are they?
Special Maclaurin.
Maclaurins. Maclaurins are only Taylors centered around. What if you're centered anywhere else?
Oh, right.
You have to build it. You have to build it from the ground up from the Taylor polynomial. Only Maclaurins get to use this special trick. Bye, guys. See you later. But if you build it, look for patterns.
You really went